Right.
Uh,
Any questions?
Not a question.
Where's
but,
the address of your GitHub?
Where my GitHub is, yes, of course. I paste the link to the repository in the chat. So where is it? There's another one. Okay, here we go.
You know, the operation system I mentioned is totally based on packages and containers. It uses Docker. And one of the things that I have on my schedule was to try to figure out how to create my own Docker containers because I have a bunch of force. And if I create them as Docker containers, it'd be easier for the system to deal with them.
Yeah, that's right.
And, well, you saved me a lot of time here.
Yeah, thanks, Alex. It looks like the same URL. Great, yeah. And now you have lots of blueprints on what you need to do. There are some systems that are right tricky, like the 386 versions to make them run on a modern 64-bit system. You have to add i386 support and the appropriate libraries and so on. And you find the recipes how to do that also in the appropriate Docker files. Yeah, so there's this 32-bit GeForce, and that was actually really a stunt to do that, where you have to do install the multi-architecture support and then also the 32-bit things. Yeah. Any other questions?
Yes, I have a question.
Yeah.
Do the Docker run on any platform or just x86?
Yeah.
I mean, would they run on Raspberry Pi maybe? Or
my
future version?
Yeah, my understanding is, well, the containers share all the kernel of the surrounding system. Yeah, so also the execution environment, more or less. The containers are more or less shields from managing access, process and file system and memory access and so on. So there are different flavors of containers. So on in a Windows world, for example, you have containers that run the Windows execution environment, and then you have Windows-like containers. And on a Raspberry Pi, which has an ARM CPU, you get Linux, but it's all ARM binaries, which if the system is actually written in C or so, then it wouldn't make a difference. So GeForce and PFE, for example, you would just compile on the Raspberry Pi and have ARM images then to execute. That would work. I think there is Docker support for the Raspberry Pi, but the images are not interchangeable.
Right. Okay, I would definitely have a look at your repo and maybe try to do a pull request to add Alex Forth to it.
Yeah, great. I look forward to that. Right.
Ulrich?
Yeah.
You're probably the right person to answer a question I had on my mind for quite a while. What's
Go
the
ahead.
main difference between Docker and a VirtualBox machine?
Yeah. Right. A virtual machine. I said containers are some kind of virtual machine. Well, it's a virtual execution environment. But the difference is that containers are more lightweight and they use the operating system kernel of the underlying system. Whereas a VirtualBox virtual machine is actually using whatever it emulates. So you can run a completely different system like a Windows inside a VirtualBox virtual machine, which has a Windows kernel. But if you have a Docker container, that it always uses the kernel of the underlying system. So if you run on a Linux x86, your containers will be x86 Linux containers. Yeah, and they all share the same kernel, and that's the main difference. Yeah.
So the Docker runs on the hardware that you have?
Yeah, and the kernel is not emulated, whereas with VirtualBox or VMware or what have you, Parallels, the hardware is emulated, the CPU in some hardware-supported virtualization mode, but it also emulates the operating system kernel, or runs the operating system kernel on the virtualized hardware. And that's with Docker, that's not the case.
Okay, thank you.
You're welcome. All right. So thank you very much. And I skip over to the schedule. So next speaker will be Virgil, and we'll learn more about Collapse-OS and Dusk-OS, sorry, and the C part, tokenizing and things like that. Virgil, please go ahead.
Yes, hello. So yeah, last time, the last presentation, we saw the harmonized assembly layer. Now we're ready to dive into the C compiler. So yeah, so today I want to cover the whole process of compiling a C file. I'll go over tokenization and expression parsing, because that's quite a big subject. So I will share my screen. Set screen. Yeah, this thing here. Yes. Right.
That works.
Do you see? Yes.
Yes.
All right. So in the previous presentation, I was using emulation, QEMU, to emulate Dusk. But since the last presentation, there was a new development in Dusk called user mode Dusk, which allows Dusk to run natively on the system. So that's user mode Dusk in its cursed flavor that I'm going to use. So you all see this. So my machine is an i386, is an Intel CPU. So this user mode Dusk is running in i386. So the C compiler. So I have this this file. Oops. All right. So I have this. I have this file that is a simple C function that I call my adder, that simply adds A and B, and I'm going to compile it because before I talk about the tokenization and the expression parsing, I just want to show you how we compile a file on a C file in Dusk. So we're going to load the compiler. All right, and we're to compile a file. It's you use that word cc bracket and then the name of the file to compile, and that will create a word that is called my adder that I can use this way. All right, so this so the compiled C file is the compiled C word can be used as any other fourth word. And you know, in the previous presentation, I was making extensive use of the disassembler to show the result of my of what I was doing, and I'll do the same here. So I'll load my disassembler because as I was telling you, this is so this runs natively on my machine, but it's an i386 machine. So what was compiled was i386 code. So if I do my adder this, we will see that the code here that was compiled is rather straightforward. So if you remember on Dusk, ESI is PSP, ESP is RSP, and EAX is top of stack. So in all C words, I extensively use the work register, the top of stack as a work register. So I always take some wiggle room. I make some wiggle room here with the dupe so that I can use EAX freely in further compiled word. So every C word starts with this, and then my parameters that were supplied here end up in ESI and ESI plus 4, and this is exactly what I do. I do a move of ESI plus 4, which will be 12, and then I add to it ESI plus 0, which will be 23. And the result ends up in EAX, which is top of stack. And all I need to do afterwards is to nip those two parameters that I've just received and return. So what I'm showing you is a bit like what I was showing you when I was telling you about the HAL. It's pretty much the same thing. So this is how functionally the C compiler works. And now I'd like to dive in with you as to what mechanisms allow us to compile the C file. So to show you that my compiler is modular, I'll restart Dusk so that you know that we're running on a clean slate here, because I will load parts of my C compiler to tokenize and to parse expressions. So first of all, tokenization. So we'll show it right there. Console self. No, sorry. I'll open the file here. All right. So you'll remember that this is the C file that we're trying to tokenize. So let's tokenize it, and let's start with a naive approach, which is to just use Word. So what if we tokenize this with the word? So it would look like this: spit tokens, spit tokens, and it would look like this. And so wait, I'll write it and then I'll explain it. While word. Right. So this would be this. So what this does here is that it checks if there's a word in the input stream. So as long as there's a word in the input stream, it loops, and then it gets a word, and then it types it, and there's a new line so that we can see how tokenization happens. So now we can do this spit tux. So the exact word here is in Dusk. The input stream is very easily overwritten, so we can hijack the input stream how we want, and this is a feature that I use a lot in Dusk. So what this does is that it hijacks the input stream with the contents of foo.c and calls spit tux, which means that when we call word, our input stream is this. So, and then as long as there's an input stream, we'll loop, and then when we stop looping, when the word returns, then we close the file and we're done. So what happens here is that I read word, and we see that there's a problem here, because my word boundaries of fourth don't work with C, because the tokenization is C has to know about the symbols it will read. So to do tokenization in fourth, then we need to build a tokenizer. So so this is what we're going to do. In Dusk, I have a general purpose tokenizer, which is in a tuck. And with this is just an API for fancier tokenizer that will go over it. And this API looks like this. Tuck Q while S type. All right, so this is the same word using the tokenizer API, and this is the important word, that is go fetch the next token using whatever method has been installed, and unless there's nothing to consume anymore, in which case we yield 0. So that makes this thing work. By default, the general purpose tokenizer is the equivalent of Word. So if we repeat that thing we've been doing, we will get the same result because the generic tokenizer is a Word tokenizer. However, we have a C tokenizer here that we can load. And now I won't show you the code because showing code in a presentation like this is meaningless, because it is anyway. I won't show you the code, but it's like 70 lines of code or something, so it's rather simple. And so what we'll do is that we'll tell the system that we'll tell the general tokenizer that we install the C tokenizer now. So we'll repeat the same step, and we will see that tokenizing works as expected. So when it fetches my adder, then it detects that this is a symbol, and it says, "Oh, well, my identifier is done, so I'm tokenizing the next word," and so on and so on. So this is how tokenization work. We can try some fancier tokenization. For example, now for this I'll need another tool. Right now I'll tokenize strings instead of tokenizing a file. For example, if I use spit-tux on a string that will be A+++B, you will see that that my tokenizer works properly. You know, because this is a typical problem when you try to tokenize C word. That is, which plus do you add? So what is A+++B? Is it A++ space plus space B, or is it A space plus plus space? Anyway, so which one is it? And the rule for tokenizing is to be greedy. That is, you get the biggest known symbol that you can, which will be plus plus, and then we'll have the plus. So exec bracket is the same as my previous exec, except that it executes a range in memory, which is my string here. So as you see, it tokenizes properly. You know, it tokenizes the A and then the plus plus, and then the other plus, and then B, and then the semicolon. In Dusk, the tokenizer also manages macros. So macro is done at tokenizing at the tokenizing step. For example, let's say that I define a macro foo that does foo42. Then if I tokenize this spit-tux, and I've tokenized something like this, at plus exec, we will see that the macro is hijacking the input stream to then input itself into the tokenizer so that it's exactly the same as if I had typed this directly. We see that tokenizing works as expected, and we don't improperly consider this as a single token. So that's my tokenizer. And any questions so far about tokenizing? No? Am I going too fast, or am I understandable?
Yeah, I think so.
Fine
All
with
right.
me.
That's fine.
I finally understood what tokenizing means.
Does
All
the
right.
does the tokenizer yield quoted strings as a whole unit? So if you have a string between quotes, it will get one token out of it?
Wait, I didn't get the question. So the tokenizer yields strings, where the result
Yeah,
of
but
a
if in the
single
C#
token is.
file there is a string surrounded by quotes, will the whole thing be a
It's
single
a single.
token?
Yeah, we will. We can try it. So spit tokens, a string, and then my str equal a quote. Now I have to escape my quote in my string. So that the escape there is for the escape there is for this literal here.
Yeah.
All right. Hello. All right. So this will be a single token. Oh no, wait, I hit caps lock. But this time, because I'm in user mode Dusk, I can copy paste. Oh no, I forgot to close my string.
Yeah.
It's not supposed to be Dusk, but I don't know why. I haven't tested it first, but it's supposed to give a single token.
Yeah.
But I can't answer your question because I'm not sure what happens there. But it works as expected when all things considered, the string is ends up as a single token. So I'll continue with expression parsing. So when all right, so when we need to generate code for example, to generate the code that goes with A plus B, there's a problem. The main problem here is that this expression is an infix expression, and we need to apply complex rule related to operator priority and associativity and stuff like that. And this is a complex problem, and I think I came up with an elegant and simple solution to tackle that problem. And this is so this is what I'm going to show you. Oops. All right. Wait, I need a little helper word for this. I'll explain you why I need this as I use it. All right. So how do we understand this expression? Well, my approach is to reorder this expression into something that Forth likes, that is a postfix expression. So for example, here, what it does, so it tokenizes every element, and then it reorders it into something that Forths understand. That is, we push A, we push B, and then we apply plus. So why did I need show here is because the token expression parsing works by checking, by consuming tokens as long as it can build an expression. So it always needs to look forward. So that's why we need this semicolon here. Is that it's to tell the expression parser that we're done with the expression. And then if we don't drop the last token, then the token will stay unconsumed into the token queue, and it will mess up with the next expression I'm going to show you. So this is why I needed this little helper word there. So this is the general approach, and I call this sequence expression. That is to transform an infix expression into a prefix expression. So yeah, that's why I call this sequence. So of course it works with expressions that are more complex than that. For example, A plus B plus C. So oops, minus C here. What? Right. So we see that it does the expected thing in Fort, you know. So if we wanted to translate this expression to Fort, then that's how we do it. It manages priority correctly. For example, if we go with A times B plus C divided by D, then we see that wait, A times B plus C divided by D. Yeah. All right. So we see that that priorities are respected. That is that the multiplication operator has priority over the addition operator. So this is how you'd expect. And we see that parenthesis in this thing works as expected. So for example, A times B plus C divided by D. We see that here parenthesis properly overwrote the natural priority of binary operators. Now things get murky when we add the unary operators in the mix. Oh no, before I talk about unary operator, I just want to show something about assignment operator. B plus C. There's something weird with assignment. If you try it at home, you will see that assignment operator are generated in the opposite order, and there's no great the reason for this is to help the code generator generate code in the proper way. So when I go to the code generation part, you'll see that it's a lot easier. It makes the code generation part simpler if we generate the right part of the assignment before the left part. So I've inversed the sequencing on assignment operators. So that's why it's this way. Yeah, C. The unary operator also works as expected. B. So we see that we get into tricky tricky edge cases. Well, it's not so much of an edge cases because when you write C, you write that kind of stuff often. But in terms of parsing an expression, it gets complex there. And if you're using a naive parser, then you're going to get to some hair pulling in that kind of expression. But this is sequenced properly. So in this case, we start with pushing A, and then it's a binary expression. So we enter the second term here, and here we see the subscript operator is the same as a plus and a dereferencing. So this should be seen as a binary operator here, and we see that here the minus C here is generated, is sequenced as this, and so we push C, and then we apply the unary operator minus to it. And the U prefix here is because there are name clashes in the operator, so we need to be able to differentiate between them. And I had a couple of. Do I have time? I'm feeling that I'm using a lot of time. Function calling is interesting. I'm doing function calling, and then I'll stop. All right. Function calling is tricky because we need to push arguments to the stack at definite points. For example, here to call foo with those arguments, to sequence this, we need to push 42, and then we need to tell the compile. We need to tell the code generator to push it right away to the stack, so that we don't deal with it with the expression anymore. It's pushed away for the call. So this is what happens there, but and it happens in reverse order because of the calling convention in Dusk. So all arguments are reversed during the sequencing. So we begin with a call to bar that has no argument. So this is the operator for function calling, and this is the number of arguments that will be consumed by the call, and then the name of the identifier. So we call this, and then we push the result of bar, and then we push 42, and we don't push this one because this is the last one, and this is a technicality. We don't need to push the last argument, and then we call we call foo with that will consume 2 arguments, and we assign the result to the identifier A, and that's my sequencer. And I'd stop there because I'm done. Do you have any question?
Right, thank you very much. Are there any questions?
I think it will be mostly a comment. I'm really glad that I'm finally getting to the compiler integrated to Dusk-OS, because this is what impressed me when I saw it first. And I'm starting to understand better how a compiler works.
Mm-hmm.
I might have a question. Does a real compiler in C operates the same way? It has to convert infix notation into postfix. Does it do it, or
Well,
is it
this
only
is a very interesting question that I would, because when I look at the other compilers, I see that no, they don't seem to do that. They seem to go the way of complicated code. So this development here that I've just shown you is very new. I did it last week. This is a big refactoring of my C compiler that I did last week, and I think that what I just written there, this sequence expression thing, is something that can only be done well in the fourth environment, and that is way simpler than whatever TCC does. TCC is very complex. Or there was on Hacker News there was an article about from Crafting Compiler that was showing how we do expression parsing when you follow some whatever academic paper that was released by whatever dude from whatever university, and when you read that, it's overcomplicated. This is really simple compared to whatever is the norm. And this is an open question I have for everybody. This is super simple, and I don't know if anybody does that.
I think
in some way you've just proven that the postfix is a better way to do things.
Yeah, but I've been trying to think what it would take to bring this approach into, for example, a C compiler written in C, and you'd kind of have to re-implement your own forth to then generate the code that goes with it. Whereas where you're in Fort, you have your Fort, so this is the simpler approach.
Yeah, I
Okay,
think
thank you, Virgil.
there's a book called the Dragon Book, compiler design book that used to be standard text, and I mean there's a whole bunch. I mean there's a whole bunch of different steps, but I think a lot of compilers do effectively convert to postfix. I mean they're not in a text-based format, but a lot of them do sort of have to transform an infix expression with brackets to a set of operands with operators applied to them, and that sort of ends up as a postfix.
What I've seen is that.
Go ahead.
What I've seen is not that. What I've seen is you transform into an AST, and then, but the AST doesn't give you ordering. So, for example, if you have A plus B, so you have a nice structure with a tree, and then with plus, and then the first term is A, the second term is B. But then, so what I've seen is that the code generation part will dive into this into a recursive manner and stuff, and do the prioritization while it generates code, or maybe it will reorder nodes into the tree or something like that. But this is not what I've seen in the wild. But
Yeah,
maybe I haven't seen enough.
What you often do is that you use the internal representation that you build up then to do optimization, like inlining or that code elimination or things like this. And so if you just parse and generate code directly, then you have a hard time to actually do that. But it might be just fine to have a compiler that parses and tokenizes and then generates code.
Yeah,
The immediacy is great.
Yeah, I mean, obviously some compilers, depends where they put the optimizers as well, and because obviously multi-pass, with LLVM, for instance, but some of them can eliminate expressions, and it depends on what level of optimization they're doing. Backends will do, register coloring, and they'll try to use as many registers as possible and keep those registers active as long as possible. So I mean, it depends what you're trying to do, and it becomes, you ideally want to simplify the expressions. I mean, some compilers, for instance, will entirely eliminate loops. For instance, in C, you can assume that any loop is not infinite. If you've got an infinite loop, which we often have in embedded systems, for instance, technically, according to the C standard, you can eliminate those loops. So they can. There's a whole bunch of transformations they're trying to do as well as at the level. So it's a very interesting subject, but it depends how deep down the rabbit hole you want to go. Often simpler is more effective, because correct code is always better than incorrect optimized code.
Yeah, of course, but so of course, being a direct generation has its drawback with regards to the optimization that can be done. But I still do, for example, constant expressions are evaluated at runtime in Dusk C compiler. So there's a bit of optimization that I don't need an AST to do that. I can do it on the fly as I generate code. But yeah, I can't go as far as an AST. But the simplicity that I get by foregoing a bit of optimization, to me is astounding.
I agree.
When I first got started with computers, I was really interested in compilers and code optimization and code generation and all these things. So I read a lot of books on it. And then when I learned about force, it totally blew my mind how simple it could be. It seemed like the academics just loved complexity for the sake of complexity. And
Yep.
yeah, all I did was peephole optimization, but it was so much simpler and faster.
Yep.
All right. Any other questions, comments?